Okay, so think about something you do like literally every single day, probably without even giving it a second thought.
Right.
You get out of bed, you stand in line for coffee, you wait for the bus, just standing up.
Yeah, the most basic human function.
Exactly. And it feels entirely static, right? Like you're just a
Yeah.
building resting on a solid foundation. But the material we have for this deep dive actually paints a completely different picture.
It really does. It's wild.
Because human balance is not this static state. And it's definitely not just a simple reflex. It's actually a super dynamic, staggeringly high-speed sensory conversation that is happening inside your nervous system right now.
Yeah, it's a continuous biological dialogue. Maintaining your verticality, I mean, it takes almost zero conscious effort for most of us, yet it requires this massive distributed network of sensors.
Just constantly pinging each other.
Exactly. Constantly exchanging data, hierarchizing information, and adapting to the physical world on the fly.
So our mission today is to decode this biological group chat. We're going to look at the three main interlocutors, so the inner ear, the feet, and the eyes.
The big three.
The big three, and the astonishing speeds at which they communicate just to, fight gravity. And then we're going to look at how modern clinical evaluation steps in. Specifically, the work of Dr. Christophe DeLong using tools like Connexa.
Right, which allows practitioners to literally listen in on this conversation when the signals start breaking down.
Which is fascinating. But to understand how we stay upright, we first have to understand the hardware, right? The things actually generating these signals.
Yeah, so the baseline of this entire system is the inner ear. It basically operates as a highly sophisticated inertial navigation instrument.
Like the gyroscope of the human body.
Essentially, yes. It's constantly scanning the position and movement of your head in three-dimensional space. And it relies on two main components. First, you have the semicircular canals.
Yeah.
There are three of these fluid-filled loops, and they're oriented across our three dimensions of space. So when you turn your head, the fluid inside those canals moves just due to inertia.
Because the fluid lags behind the movement of the skull.
Exactly. And as it moves, it sweeps across these tiny hair cells. That physical bending of the hair generates an immediate electrical signal stating, hey, your head is pivoting at this specific velocity.
Wow. Okay, so that's rotational movement.
Right. And then you have the otolithic organs,
Yeah.
the saccule and the utricle.
And this is the part in the research that blew my mind. The sources mentioned we have actual calcium carbonate crystals just like sitting inside these organs. The otoconia.
Yeah, actual microscopic rocks in your head.
That's so crazy to me.
It is. And those crystals are incredibly sensitive to gravity.
Mm-hmm.
Because they have physical mass, they literally drag on the sensory hairs beneath them whenever you tilt your head or accelerate linearly.
Like in a car.
Right. They serve as a microscopic plumb line, giving your brain a constant, uninterrupted vector for true down.
Okay, but here's the thing. The inner ear is trapped inside a dark skull, right? It only knows what the head is doing in a vacuum.
Yeah, it has absolutely no idea what the ground beneath us actually looks like.
Right. Where is the physical anchor? And that brings us to the second talker in the group chat, the feet.
The feet define the absolute truth of the ground. The plantar skin, the ankle ligaments, the surrounding musculature, they are all just packed with mechanoreceptors.
So they establish the physical reality of your base of support.
Exactly. They tell the system if the surface is sloped, if it's slippery, rigid, soft, whatever.
So we have the head's position in space from the ear, and we have the physical truth of the ground from the feet. And the final piece of the triad is the eyes.
The verifier,
Right.
providing the broader spatial horizon.
Right, and supervising this entire setup is the brain and the cerebellum acting as the conductor, just constantly cross-referencing these incoming signals for some kind of consensus.
And that consensus is key. Instability only happens when these messages become contradictory. I mean, none of this information is interpreted in isolation.
It's all relative.
Yeah. If the incoming data stream becomes asynchronous, or what clinicians call noisy, the brain struggles to assemble a coherent picture of reality.
It's exactly like a chaotic group text message. Think about it. Imagine you're the brain, right? You're trying to coordinate a plan. The inner ear texts immediately, saying, we are moving left.
Okay.
But then a second later, the feet text, no, we are standing perfectly still on flat ground. And then the eyes chime in with, hey guys, we are in a spinning room.
Right. The brain is just left scrambling, trying to figure out who is telling the truth.
Exactly. If one sensor feeds false data or even just talks too loudly, the brain loses the thread of the conversation.
And the brain's job is complicated by a massive logistical hurdle within the nervous system itself. These three interlocutors, They operate in entirely different time zones.
Oh, the biological lag.
Yeah, they do not transmit their data at the same speed at all.
Let's break down these transmission speeds because the underlying biology here is just wild. So the inner ear, that's the sprinter.
The sprinter, yeah. The vestibular system uses this ultra-short 3-neuron circuit. It takes only about 7 to 10 milliseconds to send its signal to the brainstem.
7 to 10 milliseconds.
It is wired for pure survival.
Right.
I mean, before you are even consciously aware of a bump or a perturbation, the inner ear has already dispatched the stabilization order.
Okay, then we have the feet, the hurdler. Proprioception from the feet takes about 30 to 40 milliseconds.
Which is fast, but
But that electrical impulse physically has to travel up the sciatic nerve from the very bottom of your foot, travel over a meter up the leg, and finally reach the spinal cord.
it's actually a remarkable speed for the distance involved. It relies on highly myelinated nerve fibers,
Yeah.
but it is fundamentally less direct than the cranial nerves of the inner ear, which are sitting right next to the processing centers.
Right, location matters. And finally, we have the walker, vision. In this specific neurological context, vision is incredibly slow.
Very slow.
It takes roughly 70 to 100 milliseconds.
Because the visual pathway is just far more complex. Photons must enter the eye, hit the retina, trigger a photochemical reaction, be converted into an electrical signal,
It's a whole process.
travel down the optic nerve to the visual cortex, be
Yeah.
rendered into a spatial map, and then finally be compared with the vestibular and proprioceptive data. It arrives last to the meeting.
Which brings us to how the body compensates for this huge time discrepancy. The vestibulo-ocular reflex, or VOR, the material calls this the ultimate link between the ultra-fast inner ear and the much slower eyes.
The VOR is just a flawless synchronization. So if your vestibular system detects your head turning to the right at 100 degrees per second, the vestibular nuclei in the brainstem instantly fire signals to the extraocular muscles controlling your eyes.
Okay.
And they drive the eyes to counter-rotate to the left at exactly 100 degrees per second.
100% gain, like
Yeah.
a perfect 1-to-1 ratio.
Exactly. And it executes in that 7 to 10 millisecond window, bypassing the slow visual cortex entirely.
Wait, so your eyes are being mechanically driven by your inner ear long before your brain actually sees the movement.
Yes, this reflex is why you can read a street sign while jogging. If this reflex loses its calibration, even just slightly, the visual field slips across the retina with every single footstep. It renders the world a blurry, nauseating mess.
Okay, wait, I'm confused though. If the eyes are the absolute slowest sense in this entire group chat, taking a full 100 milliseconds to process, why does turning the lights off in the shower suddenly make me feel like I'm going to fall over?
It's a great question.
Like, why do the eyes feel like the boss of our balance if they are literally the slowest ones to speak?
Well, that highlights a critical vulnerability in human neurology. We are highly visual primates, right? Our conscious perception of the world is entirely dominated by our eyes.
Sure.
But in the context of pure mechanical balance, relying heavily on vision is actually a slow trap. The problem arises when the faster primary signals, like the sharp, crisp proprioceptive data from the feet, begin to degrade.
Like from neuropathy or poor circulation?
Or just general aging, exactly. The brain loses that high-speed feed from the ground.
So it defaults to the slow feed.
Yes. It leans heavily on the eyes because vision feels like the only robust data stream left. But because vision operates on that 100 millisecond delay, the motor responses are always lagging just a fraction of a second behind reality.
The body becomes completely dependent on a delayed broadcast.
Precisely. When someone with diminished foot sensation closes their eyes in the shower, they aren't just losing a secondary sensor. They're losing the visual crutch they've been heavily relying on to mask their failing proprioception.
Wow. Which explains why these millisecond discrepancies are literally a matter of life and death. Because the entire system is engaged in a permanent race against an adversary that never, ever sleeps. Gravity.
Gravity does not pause while your visual cortex processes a shifting horizon. The precise fraction of a second your center of gravity breaches the boundary of your base of support, physics takes over.
You're going down.
Acceleration toward the floor begins immediately.
So once the sensors actually register that tilt, the motor system has to execute a recovery fast enough to outpace that gravitational acceleration. And our sources break down these motor responses into 3 distinct tiers.
Right.
First line of defense, we've got spinal reflexes. These clock in at 30 to 50 milliseconds.
These are monosynaptic loops. The stretched sensory receptor in the ankle talks directly to the spinal cord, which immediately fires a motor command right back to the ankle musculature.
The signal never even travels to the brain.
Never reaches it. If your foot begins to invert on an uneven surface, the peroneal muscles contract forcefully to protect the joint before the actual sensation of the twist even registers in your consciousness.
Okay, second line of defense, postural synergies. These take 80 to 120 milliseconds.
These are highly complex automatic motor programs orchestrated by the brainstem and cerebellum.
It's a coordinated chain reaction. The ankle adjusts, the hips countersway, the trunk engages, and the arms might extend.
Just automatically. All firing in a logical sequence to corral your shifting center of mass and bring it back over your feet.
And then the third line, voluntary movement, taking over 200 milliseconds. And the research is definitive on this. If you have to consciously think about catching your balance, you are already on the floor.
It's too late.
Voluntary movement is a death sentence for balance.
The signal routing simply takes too long. I mean, it has to ascend to the motor cortex. A conscious correction must be planned, validated, and transmitted all the way back down the spinal cord.
Yeah.
By the time the muscle actually receives the order, the gravitational acceleration has outpaced your physical capacity to recover. The data notes that dropping a reaction time from 100 milliseconds down to 200 milliseconds physically triples the statistical risk of a fall.
Triples. Just from a 1/10 of a second delay.
It's unforgiving.
To beat that brutal physics equation, human biology relies on an absolute miracle of an internal highway. The type I nerve fibers, carrying that crucial proprioceptive data from your feet. They transmit electrical impulses at a blistering 80 to 120 meters per second.
Which translates to over 400 kilometers per hour.
400 kilometers per hour inside your leg just to keep you from toppling over while you stand there checking your phone.
It's incredible engineering.
It is. But this hyper-reactive hair trigger system brings up a really obvious contradiction for me.
What's that?
If our neurology is wired to react with maximum alarm to the slightest unexpected movement, why do we trigger our own emergency reflexes when we simply choose to take a step? Like, if my inner ear feels my head surging forward, why doesn't my body panic and throw my arms out?
That paradox is resolved by a fascinating neurological mechanism known as the efference copy.
The brain finishing its own sentences. Explain how this physically works.
Okay, so when your motor cortex formulates the decision to walk, it fires the primary motor command down the spinal cord to the muscles of the legs.
Right.
But simultaneously, collateral neural pathways branch off from that main signal. They route a CC, a carbon copy of that exact motor command, directly into the sensory processing centers of the cerebellum and the vestibular nuclei.
It's literally sending a memo. Attention, I am initiating forward movement. Do not panic when the vestibular fluid shifts and the visual horizon starts scrolling.
That's exactly it. The sensory centers receive the efference copy and actively suppress the expected sensory feedback. The movement is anticipated, so the alarm bells are just muted. But consider the mechanics of slipping on a patch of ice.
Right. There is no memo for this slip.
No efference copy was generated because the slip wasn't planned. So suddenly, the inner ear and the eyes flood the brainstem with massive acceleration signals, but there is a complete silence of anticipation from the motor cortex.
Oh.
And that exact discrepancy, the presence of severe movement data without a matching efference copy, is the specific trigger for those violent 20-millisecond protective reflexes.
You know, it makes me think of warning your roommate before you turn on a really loud blender.
Okay, I like that.
If you say, hey, cover your ears, turning on the blender, they don't jump when the motor screams. But if that exact same blender turns on by itself in the pitch black middle of the night, total physiological panic, heart rate spikes, adrenaline dumps. The sensory input is identical, but the lack of expectation changes everything.
That's a perfect analogy. The biological reality of the efference copy proves that maintaining equilibrium isn't passive. Your central nervous system actually functions as a predictive engine. It's constantly running complex math to subtract self-generated movement from external environmental forces.
So if the inner ear is like the liar, actively feeding false data when those calcium crystals get dislodged, what happens when a sensor just fades out, like with aging or neuropathy in the feet? The material outlines this as the second major pathology, the background noise.
Yeah. When the mechanoreceptors in the plantar skin degrade, the sharp, high-fidelity signal from the ground turns into muffled static. And the brain requires consensus to maintain balance.
Right.
So to compensate for the weak signal, it has to work exhausting neurological overtime to try and turn up the volume on the feet.
Which leads right into the third pathology, the visual trap. Because the feet are producing nothing but static, the brain essentially cuts their microphone and goes all in on the slow visual data.
Exact.
Suddenly, walking through a moving crowd or, navigating a poorly lit hallway becomes a total nightmare because your primary source of balance is easily tricked by shifting shadows and moving objects.
And this is where the landscape of clinical evaluation has fundamentally shifted, largely driven by practitioners like Dr. Christophe DeLong and the integration of technologies like Conexa.
Yeah.
Historically, assessing a patient's balance might have been as rudimentary as checking leg strength or timing how long they can stand on one foot.
Right. But Conexa doesn't just measure brute force. It measures the quality of the sensory conversation itself. How does a clinician actually extract that data from a patient?
Well, the patient typically stands on a highly sensitive, dynamic posturography platform, basically a specialized force plate.
Okay.
This platform can precisely measure the patient's center of pressure at hundreds of hertz, capturing micro adjustments that the human eye just cannot see. By introducing controlled physical perturbations, perhaps the plate tilts unexpectedly, or the visual environment is suddenly altered. The Conexa software quantifies the exact parameters of the biological dialogue.
So it's measuring the speed of response, like the exact delay between the platform shifting and the muscles firing to correct the posture. And if that delay has crept from 100 up to 200 milliseconds, Dr. DeLong knows the sensory routing is degraded and the fall risk has spiked.
Exactly.
Mhm.
And it also analyzes the coherence of the postural synergies. The force plate data reveals whether the ankles, knees, and hips are firing in a logical, coordinated sequence, or if the central nervous system is just misfiring, sending out chaotic, poorly timed corrections. Furthermore, it quantifies what clinicians refer to as sensory listening.
By measuring the physical oscillations, right? The actual physical sway of the patient's center of mass.
Yes, when a patient is swaying excessively while simply trying to stand still, the platform maps that erratic center of pressure. It indicates the brain is struggling under a high cognitive load, desperately attempting to filter out the neurological static to locate a true vertical signal.
Which brings us to a highly practical yet totally surprising intervention highlighted in the research, the barefoot solution. We discussed the mechanoreceptors in the plantar skin earlier. The sources describe the sole of the foot as the most sensitive microphone in the entire anatomical system.
Oh, the density of sensory nerves there is staggering. They can detect a microslip of less than a single millimeter.
Unbelievable.
They register pressure variations down to a single gram. They feel the texture of the ground and the onset of a slip long before any muscle is stretched, where the inner ear detects a shift in the head. It is the ultimate early warning detection grid.
But everyday footwear introduces a massive barrier. If the feet are high-fidelity microphones, thick rubber soles aren't just static, they are heavy, soundproofing blankets thrown over the mics.
It's exactly what they are.
They absorb and filter out all the vital micro-variations and sheer forces of the ground.
And from a therapeutic perspective, this is why rehabilitation protocols, such as those utilized by Dr. DeLong, frequently involve executing exercises completely barefoot, often on unstable or textured surfaces.
To force the system to wake up.
Yeah, it forces the central nervous system to re-engage with that muscled sensory channel. It's like removing the soundproofing blanket so the brain can actually hear the high-fidelity input again. Working barefoot actively restores the audio fidelity of the sensory dialogue between the plantar receptors and the cerebellum.
The concept of sensory noise causing literal cognitive exhaustion is profound. The brain is burning so much metabolic energy just trying to filter the static to stay upright. Are heavily padded modern shoes actually making us mentally tired?
It is a serious physiological consideration. Neurological bandwidth is finite. When the sensory signals are crisp and immediate, like when you have direct barefoot contact with the ground, the brain processes equilibrium subconsciously. The cerebellum handles it, freeing up the higher cortical areas.
Right.
But when that signal is muffled by thick outsoles or degraded by neuropathy, balance demands conscious effort. You lose the ability to easily dual task, such as walking while holding a complex conversation, because the brain is forcibly dedicating vast amounts of processing power merely to prevent gravity from pulling you to the floor.
The major takeaway from all of this is that balance rehabilitation isn't just about doing heavy squats to build brute muscle force.
Brute strength cannot compensate for a 200 millisecond delay in the neurological signal. It just can't. Rehabilitation is about reducing the sensory noise. The goal of using advanced diagnostics like Conexa is to map the specific deficits, allowing the clinician to recalibrate the gain of each sensor.
Filtering out the vestibular lies and turning up the volume on the proprioception.
Exactly. The ultimate objective of therapy is restoring trust between those biological interlocutors, so the dialogue becomes subconscious once again.
So the next time you stand up to grab a glass of water, just take a second to appreciate the absolute miracle happening in the background. Your inner ear is calculating three-dimensional inertia, your eyes are locking onto the spatial horizon, and the nerves in your legs are firing data at 400 kilometers per hour. It is a flawless, invisible symphony playing out every single time you shift your weight.
It really serves as a reminder that we do not merely exist within an environment. Our nervous systems are engaged in a constant high-speed negotiation with the physical forces of the world around us.
And it leaves you with a pretty wild thought to mull over. If our feet truly are the most sensitive microphones in our entire biological setup, capable of feeling the weight of a single gram or the shift of a fraction of a millimeter, what happens to a lifetime of those crucial sensory conversations when we trap those microphones inside heavily padded sneakers every single day? Are we walking through our entire lives with our most important sensors stuck on mute?